These are the Lesson 22 activities for college algebra. Use the 5-step strategy illustrated in the demo to graph f of x equals x cubed minus x squared minus 6x. So we start by determining the end behavior. We have a positive leading coefficient, which means right arm up. We have an odd degree, which means that the left side and the right side do opposite things. So I have right arm up, left arm down. So as x goes to a negative infinity, f of x goes to negative infinity. And as x goes to infinity, f of x goes up to infinity. Find the x-intercepts by setting the function equal to 0. So I have x cubed minus x squared minus 6x equals 0. I have at least an x in every single term, so I can factor one out. So I have x times x squared minus x minus 6 equals 0. That can factor further. I have x times x minus 3 times x plus 2 equals 0. I set each factor equal to 0. And then solve each one. So I have x equals 0, x equals 3, and x equals negative 2. Each one has multiplicity 1. They all had just a degree 1 on them with their factors. So x-intercepts are at 0, 3, and negative 2. They all have odd multiplicity because the multiplicity is 1 for all of them, which means we cross the x-axis. To find the y-intercept, I'm going to plug 0 in for all my x's, so I would have 0 cubed minus 0 squared minus 6 times 0, which is 0. Symmetry. Let's see. F of negative x would be negative x cubed minus negative x squared minus 6 times negative x. That gives me negative x cubed minus x squared plus 6x. Is this exactly the function I started with? No, because my original function was an x cubed. Now I have a negative x cubed. Is this exactly opposite of the function I started with? So I had a positive, now I have a negative. This sign is negative, it's still negative. So it is not exactly the opposite of what I started with either. So this is a no, and this is a no. Maximum number of extrema would be 1 less than the degree, 2 in this case. So my x-intercepts are at 0, 3, and negative 2. You know what, I'm going to make the scale a little bigger. So I have 0, 1, 2, 3, and negative 2 will be here. Okay, and then I know it's right arm up, left arm down. And then it has to cross through the x-axis at every 0. So it's got to go down and up and back down like that, because it has to go through at every 0. Number 2, again, we're going to use the 5-step strategy to graph this function, f of x equals negative x squared times x plus 2 times x minus 2. To determine end behavior, it might be helpful to multiply this out. So I have negative x squared times x squared minus 4, and then distribute the negative x squared, and we have negative x to the 4th plus 4x squared. So I have a negative leading coefficient, which means right arm down. I have an even degree, which means both arms do the same thing. So both arms are down here, so my end behavior is negative infinity to the right and to the left. To find the zeros, I set the function equal to 0. So negative x squared times x plus 2 times x minus 2 equals 0. And it's already in factored form, so that's so helpful. I can now just set each factor equal to 0. Negative x squared equals 0, or x plus 2 equals 0, or x minus 2 equals 0. So here I get x equals 0, multiplicity 2, because of the squared. It's multiplicity 2. Here I have x plus 2 equals 0, so x equals negative 2. That only happens once, multiplicity 1. And then x minus 2 equals 0, so I get x equals 2, Again, multiplicity 1 because that's a factor with an exponent of 1. So my zeros are at 0, which has a multiplicity of 2, which means it's even. And that means it bounces off the axis. And then my next 0 is -2 with odd multiplicity, which means it crosses the x-axis. And then x equals 2, which is, again, odd multiplicity because it's multiplicity 1, which means it crosses the x-axis. The y-intercept we get by plugging 0 in for x, and I get -0 squared times 0 plus 2 times 0 minus 2, which is 0. So I'm going to plot my points. I have x-intercepts at 0, 2, and -2. My end behavior is both arms down. And then what happens in between, I'm starting to see that this might looks like I have symmetry, right? I have x-intercepts that are symmetric. Both arms are doing the same thing to the right and the left. I might have some symmetry. Let's check it. So if I do f of -x, I'm going to use this format of the original function, replace each of these x's with a -x. So I have -x to the fourth, negative x to the fourth, plus 4 times -x squared. So that gives me -x to the fourth plus 4x squared, which is exactly my original function. So I do have y-axis symmetry. I don't have origin symmetry. Okay, so I have y-axis symmetry, so that helps. I know that my zeros at -2 and 2 have to cross the x-axis, so I have to actually go through the axis, not bounce off, but I bounce off at the 0, so it's going to do something like that. And we have the y-axis symmetry. Oh, find maximum number of extrema. It's degree 4, so the maximum number of extrema is 3, and that fits 1, 2, 3 extrema. Number 3, sketch a graph of a polynomial that satisfies the conditions. So it's got to be degree 3 with 3 real zeros. Each one has multiplicity 1, and it has a positive leading coefficient. Okay, so positive leading coefficient in degree 3 means that the end behavior looks like this. Okay, and 3 real zeros, each with multiplicity 1. So I'm just going to randomly pick 3 real zeros here. And if they have multiplicity 1, that means you have to go through the x-axis. So this has to go up like that. And then we have to go through the axis, come back up, through the axis, come back down, and go down like that. Part B, degree 4 with 2 real zeros. Each one has multiplicity 2. That means they're both going to be bounce-offs and a negative leading coefficient. So degree 4 with negative leading coefficient is both arms down. And I only have 2 real zeros, so I'll do 1 here and 1 over here. Both arms have to be down, and I have to have a bounce off at those 2 real zeros. So something like that. Number 4. Earlier this semester, we used linear regression models, which are lines of best fit. Now we're going to move on to polynomial regression models, which we'll use when the data is not very linear. So the table below shows the number of women in the full-time civilian labor force in millions with children under the age of 6 for selected years. And I have a scatter plot of the data, and I use GeoGebra to create a line of best fit, and a quadratic of best fit, or a parabola of best fit. The equations are right here. The equation of the regression line and the equation of the parabola. So I want to use those two models to predict the number of working women with children below 6 in 2011. Okay, so we have year 0 is going to be 1975. The first, oh, no, it's 1970. So the first data point is 5, comma 4.8, right? So that's year 5. So it looks like we're using year 0 is 1970. So let's make a little note here. X equals 0 is 1970. So 2011 would be 41 years later. So I want to plug 41 in for my x's into each of these. So I'm going to have y hat equals 0.2111 times 41 plus 3.9919. And that comes out to 12.647 million women. Do the same thing for the parabolic model for 41 years later, and I get y hat equals negative 0.0048 times 41 squared plus 0.3799 times 41 plus 2.8662, and that comes out to 10.3733, again, million women. So graphically, we're looking at about year 41. So the parabola gives about 10-something million. The line predicts 12-something million. So using the leading coefficient test to determine the end behavior to the far right for each model, I want to think about which will be most accurate in modeling the future number of women in the civilian workforce. So for the line, it is a first degree, which is odd, positive leading coefficient, which means right arm up, left arm down. And for the quadratic, it's a even degree with a negative leading coefficient, which means both arms down. Okay, so I'm interested in the future, so the far right end behavior. So the linear model shows an increase, and the quadratic model shows a decrease in the long-term prediction for number of women in the workforce with children under 6 years old. So I think it's really hard to know here. The trend has been upwards. There's not really any indication that it would come back down, but you never really can make a good prediction about there's something societal could happen where where women end up staying not participating in the workforce when they have young children. Something like a global pandemic that forced a lot of women out of the workforce. So it's really hard to predict. There's no right or wrong answer here. Number 5, consider the scatter plot below. What degree polynomial would you choose to model this data? So hint, think about the number of turning points. So if we were to make a model for this data, it would look something like that, right? So a polynomial of best fit that would have 3 turning points, which means I need at least degree 4 in order to capture those 3 turning points. The 4-step modeling process for polynomial regression. So step 1, we use technology to create a scatter plot of the data. So up here, that's what we started with, a random scatter plot of the data. Okay. And then we decide whether a line, a parabola, or a polynomial curve of higher degree comes close to the points. In this case, we said in order to capture the behavior of this data, we would need a degree 4 polynomial. Because the more peaks and valleys data has, the higher the degree polynomial you need. So some criteria for selecting a model. The graph of the model should fit the points well. You should use the simplest model possible. So if you can get away with a quadratic instead of a quartic, use a quadratic. Use the lowest degree possible to capture the pattern in the data. The model should make sense within the context of the real-world situation. Then you find an equation of your model choice. We let technology do this step for us. You can use Desmos or GeoGebra or a graphing calculator. Then you verify that your equation has a graph that comes close to the points in the scatter plot. If it doesn't, check for typos or calculation errors. An alternative would be to reconsider your choice of model at step 1. And then finally, you can use the equation of the model to draw conclusions, make estimates, and/or predictions. Because the end behavior of a higher degree polynomial rapidly tends to infinity or negative infinity, it will either rise or fall to the right. If you're trying to make predictions far in the future, they're usually inaccurate. So extrapolation is subject to higher risk of producing meaningless results, of getting model breakdown. All right, let's do one of these optional extra practice problems together that deal with polynomial regression. So this table gives the height of a ball thrown upwards with a velocity of 30 meters per second at various times. So a quadratic regression was performed on these data using elapsed time in seconds as x and height as y. So let's write that out. Label the axes. This is elapsed time in seconds. And then the y-axis is height of the ball. Measured in meters. And technology has provided the quadratic regression equation right here. So we have y hat equals negative 3.65 x squared plus 23.73x plus 3.76. And we want to find the vertex of the regression parabola. So that's the vertex of this equation, and explain what it means in context. Okay, so the x-coordinate of a parabola, we call it h. It's negative b over 2a. So that's going to be negative 23.73 over 2 times negative 3.65. And that comes out to approximately 3.25. And then the y-coordinate of that vertex, k, is going to be f of whatever we got for h, 3.25. F of 3.25. So I'm just plugging 3.25 in for these x's. I'm going to let my calculator do this. I get approximately 42.33. So if I mark that right here, we just found the coordinates of this pink point. The highest point on the parabola of best fit is 3.25, comma 42.33. So what does that vertex mean? Explain what it means in context. So 3.25 is a time, 42.33 is the height of the ball in meters, and that is the maximum height of the ball. So the ball reaches a maximum height of 42.33 meters at 3.25 seconds. Do you feel this model represents the data well? Yes, I think it does, because the ball does start close to the ground, and it's going to go up, hit a maximum height, and it's going to come back down. So it will represent the model well from the domain 0 to 7. Okay, once we get past when the ball hits the ground again, it doesn't just keep falling through the earth. So yes, on a limited domain.